recording. You people are not hearing any echo, right? Okay.
Can you just let me in through my other device, please?
Yes, sure. Okay. So what happened is last week I fell terribly ill and I could not take the usual Saturday class. So this is the compensated class for that. This is the week 10 lecture or not lecture, the doubt clearing class for the NPTEL course of Electric Machine 1. And I am Saptarshi De. I am a PhD scholar at IIT Bombay, Electrical Engineering Department, and my area of work is electrical machine design. Okay, so this is a regular class every Saturday 7 to 8 p.m. So tomorrow also there will be a class. This is just a compensated class for the last week. All right. So before we start about today's lecture, which will be about mostly starting and speed control, I will rectify one mistake that I did in one lecture. Actually, when I drew the flux lines, probably in the last lecture, yeah, here I carelessly drew them like this. I hope you can see. Uh, but what happened here is, if you look here, there are a lot of overlaps. Flux cannot cross like this, so they cannot be like this. So I wanted to rectify this error. They should be parallel to each other like this. Sorry for the handwriting. Like this, and they should not cross each other like this. Okay, this is one error that I made there, that flux lines never cross each other. So I drew the lines very carelessly, that's why it were like this. So it should not look like that what I drew. Anyway, one more thing is, till last week whatever concepts I discussed about DC machine, I always drew two-pole machine for simplicity. But I wanted to show you here what happens in a four-pole machine. Concept-wise, there is nothing new. Everything is same. Only thing is you have four poles. Hence, you have four brushes, right? We discussed this one day that brushes are there in the interpolar region. So if you have four poles, the brushes are placed like this. And the current sheet concept that we you remember current sheet concept, that one sheet here, other sheet here, one plus I hope it is visible, one plus sheet here, minus sheet here, and they create a flux in some way, maybe like this. The thing is, if you have change the color. If you have a four-pole machine, then you have four sheets. One sheet here, another here. Both of them are cross. Why? Because both of them are under the north pole. Similarly, you have say one sheet here. Sorry. One sheet here, another sheet here, and both of them are dot. Right. So whatever concepts about say armature reaction and all we discussed, they will be similar. So if you have flux concentration here, you will have flux concentration here, like this. So this is how a four-pole. This is nothing different from a two-pole machine. Only thing is that the same thing happens multiple times. If you look throughout the periphery of the machine, air gap of the machine, the periphery, you will see things happening multiple times, but same thing happening. Okay. So these two things are somewhat recap, not recap, modification. Alright, so what I wanted to show you here is how a real commutator looks. So if you look very closely, I will zoom in. I hope it is visible. So you see,
So
on my right, left hand side, here, I hope you can see the green line that I drew. That is the armature. I think they have cut open the field from here. So this is the armature. And on the armature, no, this is not the armature. Can you tell me how I understood this is not the armature? This is the field. See, what happens is armature looks like this. If it is this round, you have slots here. So if I look at the armature from here, I should be able to see windings on these surfaces. So this must be the field. Armature is somewhere inside, and some part of the armature winding we can see. Can you tell me what this thing is called? This part of the winding. This part of the winding is called end winding. End winding. They're called end winding. Okay. Now this is the commutator. This is the commutator. I discussed in 1 class that this part is the riser. The armature coil or armature winding ends, they are connected to the riser. This riser is nothing but a continuation of the copper strip that you can see here. So armature windings come here and end, and they are connected. So this is the commutator. You can see several segments, copper segments here. And this is the brush. Brush is not very well visible. This part you can, I think you can see a dark color area is visible. This is the brush. And this metallic part that you can see, this is the holder. This holder has a very important job. This makes sure that the brushes apply proper pressure on the commutator segments. If the pressure is more than required, then there will be lot of wear and tear on the graphite brush. You know what graphite is, right? Graphite is nothing but the nib of your pencil. Okay. So you know that they are very soft. If the pressure is more than required, there will be unnecessary wear and tear. On the other hand, if the pressure is less than required, the connection will not be proper. There will be a lot of contact resistances and a lot of sparking and all also. So these holders make sure that it is providing proper pressure on the brushes. And this is maybe some other things. This is how the end winding and the commutator of a DC machine looks. Since we talked about end winding, I want to show you one more thing here. This thing you will not see in a DC machine. This is for an induction machine. So in induction machine, what happens is, see, you still have the brushes. Brushes are still there, but inside the induction, say this is the rotor. So inside the rotor winding, the AC currents are flowing, and we need not rectify those AC currents. All we need is just the AC current outside. So there is no requirement of rectification. So we do not need a segmented copper commutator here. All we need is a continuous copper ring. This is called a slip ring. This is a slip ring. Right? So what happened is, we will come back here. Why at all we need this segmented copper in the commutator? We discussed it in the very first or second lecture of DC machine, that the current in the armature of DC machine, that is not a DC current. How do I know? Say for example, you look at this conductor. Right now this conductor is carrying a dot current, means the current is coming towards us. Now it is rotating in this way. As soon as it comes here, the current becomes zero. Then when it comes under the influence of the north pole, the current becomes cross, flowing away from us. So from outside, it looks like the current should be stationary. It is stationary. But if you look at one winding, their current is alternating. But it is a DC motor. I want DC current outside, or I want to supply DC current. That is why this commutator is required. So very interestingly, it is said that this brush gear plus commutator system. So what happens in a DC motor? DC motor, we are supplying electrical power from outside into the motor, right? So I have say DC here, I have AC here, AC current here, and the DC current is flowing through the commutator to become AC current. Then what can I say? Or can I give some other name to this brush gear commutator system? What is that thing in electrical engineering that converts DC current to AC current? Or in other words, that makes sure that power is flowing from DC side to AC side. What is that called? A black box. One side you have DC, other side you have AC, and the power is flowing from DC side to AC side. What is that called? Many of you might even have it at your home. That is called an inverter. So a DC, in case of a DC motor, the brush gear plus commutator system acts as a mechanical inverter. And on the other side, this you have to say. For generator, it is making the AC current DC. The power is now flowing from AC side to DC side. So what can I comment about it? What can I call it? In case of DC generator, a mechanical what? What is the reverse of an inverter? That makes AC to DC. It's a rectifier. Okay. It is a rectifier. So it works as a rectifier of a for a DC generator, it acts as a mechanical rectifier. Okay. So today we will mostly talk about starting and speed control of DC machine. So another question is first question is whether DC machine is self-starting or not. We will look at this diagram. Okay. So suppose that the machine is not, it's a motor. Okay. We are talking about starting and speed control. So obviously we are talking about motor, not generator. So it's a motor. We have to find out whether it is self-starting or not. First of all. So initially what we have, the motor is at standstill. No power is provided from outside. First, the field is turned on. Let us say it's a separately excited machine. Field is turned on. Okay. Now what I do is I provide DC voltage at the armature terminals. So as soon as I give the DC voltage at the armature terminals, DC not DC current, we see that the motor is drawing DC current.
Sir, this is self-starting.
Yes, it's self-starting. We will just look at it how we know it is self-starting. So as soon
So
as
as
we
soon as
put
we put
DC
DC
voltage,
voltage,
these
these
windings
windings
start
start
carrying
carrying
current,
current,
and
and
we can
we can
apply
apply
F
F
equals
equals
Q into
Q
V
into
cross
V
B.
cross B.
Right?
Right?
This
This
exercise we
exercise
did,
we did,
that if
that
current
if
is
current
flowing
is
in
flowing
this
in this
direction, then
direction,
what
then
did
what
way
did
the
way
rotor
the
will
rotor
rotate.
will rotate.
So it will start
So it
rotating.
will start rotating.
So it is
So
a
it is a
self-starting machine.
self-starting machine.
Then why at all
Then why at all
do we need a
do we need a
starter
starter
for a DC
for a
machine?
DC machine?
We will
We
see.
will see.
I don't know. Okay, anyway. I am completely on a new device today. So why at
So
all
why
do
at
we
all
need
do we
a
need a
starter?
starter?
40 insert space. Okay, anyway, sorry for the
Okay, anyway, sorry
disturbance.
for the disturbance.
The thing is,
The thing is,
we discussed
we
this thing
discussed this
some
thing
class
some
back,
class back,
that
that
armature
armature
resistance
resistance
of a
of
DC
a
machine
DC
or
machine or
any
any
machine
machine
is
is
negligible,
negligible.
right?
Right?
You have
You have
solid
solid
copper
copper
windings,
windings.
you wound
You
them
wound them
and make the
and make
armature
the
out of it.
armature out of it.
Okay,
Okay.
so all
So
the resistance
all
you
the
have is
resistance
only
you
the
have is
resistance of
only the
copper.
resistance of copper.
That is very
That is
less, very small.
very small.
Now,
Now,
if this
if
is
this
the
is the
equivalent circuit
equivalent
of a
circuit
DC
of a
machine,
DC machine,
this is the
this is
lump
the lump
resistance, lump
lump
armature
armature
resistance. We discussed this,
this.
that
That
actually
actually
we
we
cannot
cannot
reach
reach
this
this
terminal.
terminal.
This whole
This whole
resistance is
resistance is
distributed
distributed
throughout the
throughout the
armature.
armature.
All we can
All
access
we
is
can
these two
access is these
terminals.
terminals.
Okay, so
So
I have
I
my
have my
terminal
terminal
voltage V.
voltage V.
Say this is a
So this is a
motor,
motor.
it is
It is
running.
running.
So we
So
have a
we
back
have a
EMF
back
E
EMF E
and a
and
current
a
flowing.
current flowing.
This is the
This is
resistance
the
R.
resistance R.
So what is the
So what is the
current?
current?
Current is
Current is
definitely V
definitely
minus
V
E
minus E
by R,
by R.
right?
Right.
Now
Now
this
this
E
E
is
is
K
K
phi
phi
omega.
omega.
We have
We
turned
have
on the
turned
field.
on the field.
So phi
So
is
phi
there,
is
K
there,
is
K
there,
is there,
but the
but the
machine we
machine
have not
we
yet
have not yet
started.
started.
So when
So
we were
when
just
you were
starting
just
the
starting the
machine,
machine,
this E
this
is
E
almost
is
zero.
almost zero.
So
So
the
the
starting
starting
current
current
is
is
V by
V
R,
by R,
and this
and
R
this
is
R
very
is
very
very
small,
very small,
very small.
very small.
Okay. Just- yeah. So if you
So if
have
you have
applied the full
applied the full
voltage
voltage
across the
across
terminals
the
of the
terminals of
machine,
the machine,
and if
and
you
if
have
you have
very small
very small
resistance, no
resistance,
back
no
EMF
back
is
EMF
there,
is there,
so this
so this
armature
armature
will
will
draw a
draw a
large current.
large current.
What do I
What
mean
do
by
I mean by
large current?
large current?
I mean
I
by
mean
large
by
current
large
is
current is
a
a
current that is
current that
far
is far
more than
more
its
than its
than the
than
rated
the
value.
rated value.
Maybe the
Maybe the
armature is rated
armature
for
is
10
rated for 10
ampere.
ampere.
We apply the
We apply
full
the full
voltage.
voltage.
Momentarily it
Momentarily it
draws
draws
maybe
maybe
100 or
100 or
in terms
in
of
terms of
hundreds,
hundreds,
100 to 100
100 to
ampere.
100 ampere.
Momentarily it
Momentarily
draws.
it draws.
So although
So
as soon
although
as he
it
draws the
draws the
current,
current,
torque is
torque is
developed,
developed,
but the
but the
machine has some
machine has some
inertia.
inertia.
It takes
It
time to
takes
speed
time to
up.
speed up.
So this
So
omega
this
takes
omega
time
takes
to
time
build.
to build.
Hence this
Hence
E
this
takes
E
time to
takes time
build.
to build.
So that
So
small
that small
time
time
is
is
enough
enough
to burn
to
out the
burn out the
armature.
armature.
So if
So
you
if you
simply
simply
supply a
supply
DC
a DC
motor
motor
with its
with
rated
its rated
voltage
voltage
from
from
standstill,
standstill,
the
the
chances it will
chances it will
burn. Only
only
for
for
very
very
small
small
machines
machines
it might not
it might
happen.
not happen.
Otherwise, direct
Otherwise,
online
direct online
starting
starting
will be
will be
disastrous for the
disastrous for the
machine.
machine.
So this is
So
why
this is
you
why you
cannot
cannot
start a
start
DC
a
machine
DC
directly
machine
like
directly
this.
like this.
I don't know
I don't
whether
know
you
whether you
have
have
done
done
experiments on
experiments
DC
on DC
machine in
machine
your
in your
university
university
laboratory.
laboratory.
So what we
So what
do
we
is,
do is,
in
in
starting of
starting
DC
of DC
machine,
machine,
we have
we have
potential dividers
potential
like this.
dividers like this.
Okay. wipers, and this is
and
the
this
machine
is the
terminal.
machine terminal.
So can
So
you
can you tell me?
say I will
I
write,
will write.
sorry.
Sorry.
So I
So
will
I will
write
write
maybe
maybe
terminal A
terminal
at
A
one
at
side,
one side,
B on other
B on
side,
other side,
same as
same
A
as
here,
A
B
here,
here.
B here.
The question
The
is,
question
when
is,
we are
when
starting
we are
the machine,
starting the machine,
on which
on
side
which side
should I keep
should
the
I keep
wiper,
the wiper?
A or B?
A or B?
I have
A
to
I
side,
have to link.
yeah, go on,
Yeah,
Ranjit.
go on, Ranjit.
A side, sir.
Okay.
Okay.
So we have
we have
to
to
limit
limit
the
the
starting current,
starting current,
right?
right?
Now
Now
Ranjit is saying
Ranjit
we
is
have to
saying we
put
have
it
to
on
put
A
it on
side.
A side.
Let me
Let me
remove AB
remove
from
A
here.
from here.
Just remember one
Just
thing,
remember
when
one,
I am removing this
removing
wiper
this
on
wiper
one
on
side,
one side,
the other
the
one is
other one is
also
also
removed the same
removed
way.
the
What
same
we
way.
do
What we
is,
do
with
is
our
with
two
our two
hands, we
hands we
hold two
hold two
wipers and move
wipers
them
and move
together.
them together.
So
So
if I
if I
move this
move
wiper
this
on this
wiper on
side,
this side,
so you see
so you
there
see
is
there
no
is no
resistance in the
resistance
path
in
of
the
the
path of
current.
the current.
The DC
The
machine
DC
simply
machine simply
started
started
online.
online.
So
So
we are not
we
getting
are
the
not getting
advantage
the
of it.
advantage of it.
What we have to
What
do
we have to
is,
do is
we have to
we
move
have
it
to move
on
it
this
on
side.
this side.
If we move the
If we move the
wiper,
wiper,
both the
both the
wipers
wipers
on this
on
side,
this side,
then the
then the
current
current
will have to
will
go
have to
through
go through
this
this
resistance,
resistance,
potential divider
potential divider
resistance,
resistance,
to enter
to
the
enter the
armature. So
armature.
we are
So we
having
are
a
having
lot
a
of
lot of
series
series
resistance
resistance
with the
with the
armature.
armature.
So the
So the
current will be
current will be
limited.
limited.
So in
So in
our
our
laboratories, what we
laboratories,
do
what we
is,
do
in
is in
UG,
UG,
first year,
first
second
year,
year
second
machine
year
labs
machine labs
itself,
itself.
um,
Um,
we
we
put the wipers in
put
the
the
at the
wipers
proper
in the at the
place,
proper,
turn on the supply. Okay,
turn on the supply.
then the machine does not start
Then the
rotating.
machine does not
Then
start
we
rotating.
very
Then we
gradually
very gradually
keep moving these
keep
wipers,
moving these wipers,
and the machine
and the
starts
machine
slowly.
starts slowly.
Then we
Then
gradually
we
increase,
gradually
increase.
increase.
I mean,
I
move
mean,
these
move these
wipers towards the
wipers
supply
towards the
side.
supply side.
We have a
We have a
voltage,
voltage,
voltmeter here.
voltmeter here.
Whenever it
Whenever
reaches
it
the
reaches
rated
the rated
voltage,
voltage,
we stop.
we stop.
We keep the
We keep
wipers
the
there.
wipers there.
This is how a
This is how a
DC
DC
motor
motor
is started.
is started.
Sir, network problem, so I can't understand something. Please explain me.
Network
Network
problem.
problem.
Is my
Is
voice
Hello,
my
breaking?
voice breaking?
sir. I have some network, so I can't listen here from starting.
Can you hear me
Can you
now?
hear me now?
Yes, sir. Yes, sir. Can you explain it from starting?
So there are
So there are
three
three
possibilities, not
possibilities,
three
not
possible,
three
two
possible, two
possibilities.
possibilities.
One is
One
where
is where
this blue
this
colored,
blue color,
not blue color,
not blue
same
color,
wiper,
same wiper,
this blue
this blue
position
position
or the green
or green
position,
position.
where to
Where
start
to
it from.
start it from?
If I put
If
it on
I
the
put it
blue
on the blue
position,
position,
then the
then the
current from the
current from the
supply
supply
is not
is
getting any
not getting any
resistance in its
resistance in
path.
its path.
It is
It is
simply
simply
skipping this
skipping this
resistance.
resistance.
Can you
Can you
understand which
understand which
resistance?
resistance?
Uh, this red
This red
resistance,
resistance,
this
this
potential
potential
divider
divider
resistance,
resistance,
skipping this
skipping this
and going
and
into
going
the
into the
machine.
machine.
So we are not
So we
getting
are
the
not getting the
advantage.
advantage.
What we have to
What
do
we
is,
have
we have to put the
to put
wiper
the
on the
wiper
green
on the
side.
green side.
Then the
Then the
current
current
has to
has
flow
to flow
through this
through this
resistance
resistance
to the
to the
machine,
machine,
again in the
again in
return
the
path
return path
through the
through the
resistance
resistance
to the
to the
supply.
supply.
Basically,
Basically,
two
two
resistances in
resistances in
series.
series.
So
So
what we
what
need
we
is,
need is
we need to
we need to
limit
limit
the
the
starting current.
starting current.
To do
To
that,
do that,
we have to
we
put
have to put
series
series
resistance in the
resistance in the
armature
armature
at
at
starting.
starting.
Once the machine
Once the machine
starts,
starts,
we have to
we have to
gradually reduce the
gradually reduce the
resistance
resistance
and make it
and
zero.
make it zero.
Then
Then
it is
it is
getting
getting
the
the
machine is
machine is
rotating
rotating
at its
at its
rated speed
rated
maybe.
speed maybe.
So the
So
back
the
EMF
back
is
EMF
rated,
is rated.
means
Means
E and
E
V are
and
very
V are
close
very
to each
close
other.
to each other.
So the
So the
current is
current is
small.
small.
Now when you
Now
load
when
the
you load the
machine,
machine,
the
the
speed of the
speed of
machine
the machine
drops.
drops.
As a
As
result,
a
E
result, E
drops.
drops.
So the current is V minus E by R. Loading the machine means speed is dropping. So E is dropping means current is increasing. Yeah, so what happens when you load a machine? Current increases. Right. So this is how we can start a DC motor, not damaging it. But the question is, then why at all this starter is used? This is called 3-point starter. So as you understood that starting has a considerable concern about the safety of the machine. So this starter should not only start the machine safely, but also make sure that it runs safely. That if some fault or some other thing happens during the operation, it should take steps. Okay. So this is the 3-point starter. We will understand the operation of it. Have you ever seen or used 3-point starter in your lab? Okay. So why 3-point? Because these 3 points. L, F, A. Right? What is L? L means line. Line or live. So if you have a DC supply here, plus minus, you have a switch here. Okay. You have a switch here. And this is a line. This goes here. Okay. So when this 3-point starter comes, outside the starter, it looks like this actually. Yes, Sachin, you can go ahead.
So I heard there is a something called 4-point starter.
Yes,
Hello?
4-point starter has some other advantage. As far as
No,
I
but
can
this
recall,
has been discussed by Professor. 3-point professor has discussed that. But he has not discussed the 4-point starter.
okay, I am not prepared about it today. So tomorrow I will discuss 4-point starter. Make sure you attend tomorrow's class. I will read about it and discuss. Okay. So this 3-point starter from outside looks like this. It has a cutout here, and a handle comes out, and 3 points L, F, A. So this is the armature point. Okay, in that case, should I skip this discussion about 3-point starter?
No, sir.
Okay. So this armature A point goes to armature and field goes to field. This is how a 3-point starter is connected to a machine. Okay. Now we will see the operation. First, what we do is we close the switch. As soon as you close the switch, nothing happens. Only this starter gets power. Machine does not start rotating. Now we have a handle here. This actually we have insulator handle, and we hold it to move this square thing. And it is spring loaded. Means when you move this thing in this direction, the spring opposes. We will later see why at all this is required. Now I will draw this only as a straight line. Suppose I move the starter and put it at point 1. Okay. What is happening? How is the current flowing? Current was coming. Just a minute. Okay. Current was coming, flowing like this. It flows through the solenoid. We will see why at all this is required. Flows through this, goes into this handle, and it gets two branches. First of all, the field through like this solenoid and field completes this path. You can see here there is no resistance in the field. Field resistance is not required. It is just the inductor to give voltage, starts getting current. And other part of it that is flowing through this resistance. Now you see this whole resistance is now in the path of it. So the current flows through this whole resistance, then goes to the armature and goes back to the supply. So basically when you are starting the DC machine with this 3-point starter, at your point number 1 is the point number 1, you have the full resistance in series. So the machine is now getting a very limited current, a current which is not sufficient to burn out the armature, but sufficient enough to start the machine. So what you do is you hold this handle, move it by one room. Machine starts rotating slowly. Once it starts rotating slowly, you see that it has got stable. You move it to 2. Its speed increases. 3, 4, then 5. That means you have cut out the complete resistance. There is no more resistance in series with the armature. Right? So the starting is complete. Now, okay, I will make this figure clear.
Sir, this starter is moved from 1 to 5 automatically, or we have to move it from 1 to 2
manually. There is
we
a
have to
handle.
move it. Okay.
There is a handle that you hold it and move slowly. Okay. So once you reach 5, machine has started. So your presence is no more required. But if you release the handle, the handle will again go back here. Why? Because there was a spring. The spring is required. We will see why. So to do that, to avoid that, there is a soft iron piece connected here. As you can understand, when this is rotated, this iron piece reaches here. And there was a solenoid. A current was flowing through it. The field current was flowing through it. So this is field current, is it? Yes. So this solenoid will attract this plunger and it will hold the handle there by magnetic force. So now you can release the handle. It will stay there like a magnet pulling it. So this is very simple operation of a 3-point starter. 4-point starter we will discuss tomorrow. I will prepare for it and discuss. So now the question is what I said at the beginning. The starter is not only for starting, also for protection of the machine. So two kind of protection this starter provides. First protection is OC, overcurrent. Overcurrent is overload. So what will this starter do if the machine is overloaded or for some other reason is drawing overcurrent? It will stop the machine. How will it stop? We will see. Okay. Look at this solenoid. There was an electromagnet here, right? See, the current that was coming from here was flowing through the solenoid. So the current through the solenoid is nothing but the armature current. So if there is an overcurrent in the armature, this solenoid will become more and more stronger magnet. and it will attract this piece more and
more
strongly.
strongly.
Right. So if there is
If
an
there is an
overcurrent,
overcurrent,
this
this
solenoid will become a very strong electromagnet. It will
It will
attract
attract
this plunger
this
towards
plunger
this,
towards this,
and
and
the
the
rectangle that you
rectangle
can
that you
see
can
here,
see here,
I am making
I
it
am making
green.
it green.
This is
This
made
is
of
made of
iron.
iron.
Sorry, not
Sorry,
maybe
not
iron, maybe copper, any conductive
conductive
material.
material.
So if
So
it
if it
attracts
attracts
this
this
plunger
plunger
towards it,
towards it,
this
this
iron or
iron
copper
or
piece,
copper piece,
whatever,
whatever,
it will
it
short
will short
circuit these 2
circuit these 2
points.
points.
We will see
We will
what
see what
happens if it
happens
short
if it short
circuits these 2
circuits these 2
points.
points.
So let us see
So let
what
us see
these 2
what these
points
2
go.
points go.
One is here.
One is here.
Let me draw it
Let me
with
draw
red.
it with red.
One is here.
One is here.
The other one
The
is
other
here.
one is here.
So
So
basically,
basically,
if there is a
if there is an
overcurrent,
overcurrent,
this
this
solenoid
solenoid
will be short
will be short
circuited.
circuited.
And what
And
was
what
this
was this
solenoid doing?
solenoid doing?
This was
This
simply
was simply
holding
holding
the
the
plunger,
plunger,
this handle, on the
on the
run side.
run side.
This
This
5 point is called the run. It was simply holding the
holding the
handle there.
handle there.
So if you short
So if you
circuit the
short circuit the
solenoid,
solenoid,
there is no
there is
current
no
through it.
current through it.
So the
So the
solenoid is
solenoid is
demagnetized.
demagnetized.
And
And
then what happens is this spring, which was always pulling it
pulling it
against the
against
magnet
the
force,
magnet force.
the magnet
The
force is
magnet
now
force
gone.
is now gone.
So it pulls
So
it
it
back,
pulls it back,
and the
and the
handle
handle
directly reaches here,
reaches here,
and the machine
and
is
the machine
stopped.
is stopped.
So if
So
there is
if there is
an
an
overcurrent through the
overcurrent
machine, the machine
the
will
machine
automatically stop. The
The
starter
starter
will
will
cut the machine from
cut
the
the
supply.
magnet supply.
And the
And
other
the
kind of
other kind
protection
of protection
it provides is
it
under
provides
voltage,
is under voltage,
or basically no
or
volt.
basically no volt.
See,
See,
suppose you start
suppose
the
you
machine
start the
properly.
machine properly.
Okay, machine is running.
Machine is running.
Now there is a
Now
power
there is a
cut,
power cut,
a power
a
failure,
power failure,
and the DC
and the
supply is
DC
gone.
supply is gone.
There is no DC
There is
supply.
no DC supply.
So machine will
So
stop.
machine will stop.
And
Sir,
yeah,
sir, if the starter is on 0.5, then the current will flow from 0.1 or not?
no, how can
No,
it
how
flow
can it
from
flow
point
from
1?
point 1?
Okay, I will
Okay,
draw
I
it.
will draw it.
Because of the sun are
See, if it is in
If it is in
0.5 here,
yes, sir.
then how is
then
the
how
current
is the
flowing?
current flowing?
It is
It
coming
is
from
coming from
supply
supply
through this
through this
solenoid,
solenoid,
comes here,
comes here,
goes to
goes
5,
to 5,
goes to
goes to
armature.
armature.
There are
There are C
1,
1,
2,
2,
3,
3,
4
4
resistances.
resistances.
When we are
When we are
starting,
starting,
keeping the
keeping
handle
the
at
handle at
0.1,
0.1,
all the 4
all the 4
resistances are in
resistances
series
are in
with the
series with
armature.
the armature.
Then I
Then I
put the handle
put
here.
handle here.
One
One
resistance is
resistance
gone.
is gone.
Current is now
Current is
flowing
now
through
flowing through
3
3
resistances.
resistances.
I put it
I
here.
put it here.
Current is
Current
flowing
is
through
flowing through
2
2
resistances.
resistances.
One
One
resistance,
resistance,
then no
then
resistance.
no resistance.
Machine has
Machine
properly
has properly
started.
started.
Clear?
Clear?
Okay, sir. When we change the point, then the current will cut from point.
When we are
When we are
changing,
changing,
if the
if
handle
the
is
handle is
here,
here,
connection is
connection
here,
is here,
the current
the
has to
current
flow
has to
through
flow through
like this, isn't it?
isn't it?
Now, if the
Now,
handle
if the
is
handle
here,
is here,
obviously the current
obviously
will not
current
go
will not
this
go
way.
this way.
It will go
It
like
will go
this.
like this.
So now the
So now
resistance
the
is
resistance is
reduced.
reduced.
Now when it
Now
is
when
here,
it is here,
current will flow
current
like
flow
this.
like this.
Resistance is even
Resistance is
reduced.
even reduced.
And when it is
And
here,
when it is here,
it is flowing
it is
like
flowing
this,
like this.
even more
Even more
reduced.
reduced.
Understood?
Understood?
Yes, sir. Clear.
Okay. Now what I was telling is, suppose forget the starter for some time now. What we were talking about this laboratory setup to start a DC machine. We put the wiper here, started the machine. gradually moved it towards blue side, and we left it here, and the machine was running. It was a manual thing. Now suppose there is a power cut, the DC supply is cut off, and the machine stops. No problem. But suppose the users are not there, we are not there, and again the power comes back. Now what will happen? The whole resistance is cut off, and the power has come back, full 220 volt or somewhat whatever the rated voltage is, that has come back. So that voltage will burn out the machine. It will drive large current through the armature, and it will burn out. So you have to make sure that as soon as there is a power cut, the machine is cut off from the supply, such that when the power comes back, the machine does not get the full voltage. So what we have to do is, if there is a power cut, if the DC supply is cut off, the machine must be cut off from the supply. So this plunger here, or sorry, not plunger, this solenoid here does the same job. It saved our machine from overcurrent, and if there is a power cut, this electromagnet will again demagnetize, and as a result, this spring will pull back this handle to the start side. Machine will stop. When the power comes back, the machine will not start again. You have to again go to the machine and start the machine manually. Right? So there is no chance of the machine getting damaged. Is it clear? Two kind of protection that the starter provides. Okay. So this is starting. I thought I will cover speed control. Yeah, Shashidhar, go ahead.
Sir, regarding this series motor, I think this is only for shunt motor, right?
Shunt motor.
If the series motor is there any such starter for series motor?
I have never seen as such, but what we used to do in laboratory, we used to put a series resistance with the armature and start the machine with full resistance, then gradually cut off the resistance.
But the resistor can be done, rheostat can be connected, right, sir?
Yes, that is always done.
Okay.
Actually, there are some kind of relay arrangements. You might have seen these kind of switches at your home for the pumps. You have seen these switches? They looks like a box, and you have one red switch and one green switch. To start the motor, push red. Push green. To stop the motor, you push red. So there are arrangements like this. If you have a push button, there is a. This is not a capacitor. This is a relay. And this is so like this. And the motor is here. So the idea is, say if I number it as 1, and if I number it, this one also is 1, this one also is 1. So when this coil, this is the supply. Okay. When this coil is energized, these two relays they connect. Okay. So as soon as they are connected, you see, this relay gets connected. So now you can release the push button. This coil will still get a supply, and this motor will run. And if there is a power cut, this coil will get de-energized, and the motor will stop because this relay will open. This kind of arrangement is also used. very much for induction machine, and for series machine also it can be used. This will remove the machine if there is a power. You will see if you have, don't you have such switches at your home? Or maybe somewhere you have seen. You will see if there is a power cut, the machine stops. If again the power comes back, machine doesn't start. You have to again push the button. Okay. So speed control. I will quickly do. We have a small problem also. So when we talk about speed control of any machine, keep it in mind. Not only DC machine, any machine. The speed is controlled in two regions. Say you have the base speed, say IWB, zero speed, some other speed. So zero to base speed. This is one kind of control. Above it, another kind of control. So all the machines are controlled. Speed controls are done in two regions. And the theory behind it and the performance of the machine behind it is more or less the same for almost all the machines. Be it induction machine. In induction machine, this is done in a separate way. But the ultimate outcome is the same. Okay. So how it is done? We will simply look at the equations. E equals K phi omega. Torque equals K phi I. Okay. When the machine is at zero speed, full field current is flowing. Right? That is the phi is at its rated value. Okay. Now you have the current flowing through it. You have to increase the speed of the machine. To do that, what do we do? We control the voltage of the armature. We increase the voltage of the armature. The current increases, torque increases, speed increases. So in this range, 0 to base speed, it is armature voltage control. Armature voltage control. Now you have reached the base speed. You are supplying rated voltage to the armature. Now you want more speed. Now you have to know one thing. Power is speed times torque. At base speed, you have base torque. Right? So you have rated speed, rated torque, hence rated power. You want to increase the speed even more. So your torque cannot be kept constant. Because in that case your motor has to be overrated. It has to operate at power level more than the rated value. So beyond base speed, if your speed increases, if you want to increase the speed, torque must be reduced so that the power is constant, kept constant. To do that, what is done is flux is reduced. If you look at this equation, E this is E. This is voltage V. Since the voltage is kept constant, and the current in field we can control this current more or less same as constant. So what will happen is we can write omega proportional to 1 by 5. You have to reduce the flux. If you reduce the flux, the machine speed will increase beyond its base speed. It happened in our laboratory. Sometime we were in third year. At that time, we were experimenting on DC machine. Suddenly, there was some loose connection or something. The field winding came out. The machine DC machine field got disconnected. So as a result, the flux is not zero because there is remnant flux. So you have very less flux. Means your speed has gone up extremely high. We saw in front of our eyes, suddenly the machine started getting at very high speed. We could even feel the tremor on our laboratory floor, and it was quickly stopped. So such kind of accident might happen with field. So you have to make sure that your field winding is getting full current at the starting. Otherwise, the machine will get extremely high speed. Bearings will be damaged. Machine going into very high speed has no problem with electrical engineering. It can go. But the problem is mechanical aspects. The windings might fly out. Bearings might get damaged. Okay. But the thing is, in order to go beyond base speed, we have to reduce phi. Look at this equation now. We have to reduce phi. But this current, say I was getting rated torque from the machine. So the current that the machine was drawing was rated current. Now I have reduced phi, but I cannot increase the armature current. There is a rating. Then with the armature will be damaged if I go for higher current for a long time. So this IR is fixed. IR is fixed. So to go beyond base speed, you have to reduce your torque also. What I just said just some time back. So beyond base speed, we are weakening the field. This is called field weakening zone. So if you are weakening the field, the torque capability of the motor reduces. This is very much used in electric vehicles. Nowadays, you might have heard about electric vehicle. When the electric vehicle starts, or maybe it is going up a slope, the speed is at or low or below base speed. But when you are driving your vehicle on a plain road, very high speed, the torque requirement is not that much. When I say very high speed, do not think 100, 120, say 50, 60, steadily you are driving. The torque requirement is not that high. At that point, the electric vehicle motors operate under field weakening control. They are not giving the full torque, but running at a very high speed. Okay, it's already 8 p.m. Anyway, we started late also. We will look at this problem and conclude for today. Read the problem. A 220 volt DC shunt motor. Read the problem. Is used to drive on road, which has a constant torque. Can you give me an example of constant torque load? A lift is a constant torque load. If there are 10 people inside, say is a lift, right? Say you have a wheel. Is a lift. So if there are 10 people inside, say 800 kg of people, maybe it's 100 kg of the vehicle, 900 kg is the load. Now 900 kg times this radius, that is the torque. That is the tension. Sorry, 900 is the tension, and that times the radius is the torque. Does not matter whether the carriage is moving slowly or fast. Torque is fixed. So this is a constant torque load. So 220 volt DC shunt motor is used to have a constant torque load. At no load,
No
the
load, the
motor
motor
takes
takes
1 ampere
1
armature
ampere
current,
armature current,
runs at
runs
certain
at certain
speed.
speed.
Armature resistance
Armature resistance given.
you see
You see,
such small
such
armature
small
resistance.
armature resistance.
Normally,
Normally,
when the
when
load
the
is
load is
applied,
applied,
the
the
motor takes
motor takes
25 ampere
25
current.
ampere current.
Okay,
Okay,
we will look at
we
this
look
problem.
at this problem.
You remember
You
what
remember
I
what I said
that
that
if I do
if I
not
do not
add
add
any armature resistance
resistance
and directly start the
directly
machine
start
with full voltage,
with full
then the
voltage,
starting
then the
voltage,
starting voltage,
sorry, the starting
sorry,
current
the starting current
is supply
is
voltage
supply
by
voltage by
armature
armature
resistance.
resistance.
So it is
So it is
220
220
by
by
0.5
0.5
in this
in
case,
this case,
which is
which is
440 ampere.
440 ampere.
So this
So this
machine,
machine,
when the load
when
is
the load is
applied,
applied,
takes
takes
25 ampere
25
armature
ampere
current.
armature
Say
current.
this is the
Say this
rated
is the
current.
rated current.
But if you
But if you
start this machine
machine
directly online,
online,
even on no
even
load,
on no load,
it will draw
it will draw
440 ampere of
440
current,
ampere of current.
and it takes some
And
time
it
for
takes
the
some
machine
time
to
for the machine
accelerate.
to accelerate.
That means
That
take some
means
time
take some
for
time for
the back
the
EMF
back
to
EMF to
develop.
develop.
By that time,
By that time,
it will
it
simply
will
burn
simply
out the
burn
machine.
out the machine.
How much is
How much is
440
440
by
by
25?
25?
It is more
It
than
is more than
16.
16.
17.6.
17.6.
So you are
So you are
pushing
pushing
17
17
or maybe say
or maybe say
18
18
times higher
times higher
current
current
to an
to an
armature.
armature.
Definitely it will burn.
Definitely it will.
This is why you need series resistance for
This is
start.
why you need series resistance for start.
Or you may reduce the voltage
Or
and
you
stuff,
may
whatever.
reduce the voltage and stuff, whatever.
Now
Now
suppose
suppose
a
a
3.5 ohm
3.5 ohm
resistance is
resistance is
inserted
inserted
in series with
in
the
series
armature.
with the armature.
Assume the no
Assume the
load
no
torque
load torque
is
is
constant.
constant.
Question is
Question is
estimate the no
estimate
load
the no
speed
load speed
after connecting
after
the
connecting the
resistance,
resistance,
on load
on
speed
load speed
and speed
and speed
regulation.
regulation.
Okay.
Okay.
So
So
the no load torque are
are
nothing but
nothing but
losses,
losses,
mechanical
mechanical
losses,
losses,
friction,
friction,
windage.
windage.
You know what is
You know what
windage
is
loss?
windage loss?
Viscous drag
Viscous
of the
drag
air.
of the air.
Windage loss.
Windage loss.
So
So
torque of a
torque of a
machine
machine
is
is
K
K
phi
phi
I.
I.
Okay. It is said
It is
that
said
the
that
no
the
load
no
torque
load
is
torque is
constant,
constant,
and
and
it says
it
nothing
says
about the
nothing
field.
about the field.
So we can
So
assume it
we
to be
can assume
constant.
to be constant.
So if the
So
no
if
load
the
torque is
no
constant
load torque is constant
and the
and the
flux is not
flux is
also
not
changed,
also changed,
it does not
it does not
matter
matter
whether there
whether
is
there
a
is a
series
series
resistance to the
resistance to
armature
the
or not,
armature or not.
because
Because
torque is same,
torque is same,
so it will
so
draw
it
the
will
same
draw the
no load
same no
current.
load current.
So
So
even if
even if
you are
you are
connecting a
connecting a
series
series
resistance to the
resistance to the
armature,
armature,
if the no
if
load
the no
speed
load
is
speed is
no load
no load
losses
losses
are the same,
are the same,
then
then
the no load
the no
current is
load
also
current
the
is
same.
also the same.
Okay. Now we have
Now
to
we
find
have to
out
find out
the speed.
the speed.
Very easy,
Very
right?
easy, right?
We did
We
this
did
kind of
this kind of
problems.
problems.
Now E
Now E
equals
equals
K phi
K phi
omega.
omega.
We have to
We have
find
to
out the
find
back
out the
EMF
back
in both the
EMF in both the
cases.
cases.
So in the
So in
first
the
case,
first case,
what we
what
had,
we had,
we had
we had
220 volt
220 volt
and
and
0.5 ohm
0.5
here,
ohm here,
and the current
and
flowing
current flowing
was 1
was
ampere.
1 ampere.
So
So
before
before
connecting
connecting
the armature
the armature
resistance,
resistance,
our back
our back
EMF was
EMF was
220
220
minus
minus
0.5
0.5
to
to
19.5 volt.
19.5 volt.
After connecting
After
the
connecting
armature
the armature
resistance,
resistance,
it is drawing
it
the
is
same
drawing the
current.
same current.
I'll
I'll
explain why.
explain why.
It is now
It is now
4 ohm,
4 ohm,
3.5 plus
3.5 plus
0.5.
0.5.
So now
So
our
now
back
our back
EMF is
EMF is
220 minus
220
4,
minus 4,
216 volt.
216 volt.
So
So
what we have is
what we have is
219.5
219.5
by
by
216.
216.
Our
Our
initial speed
initial
was
speed was
1100.
1100.
Our new
Our
speed will
new
be
speed will be
something.
something.
Can you
Can
do it
you
and
do
tell?
it and tell?
It's
It's
1082.
1080.
RPM.
RPM.
So
So
the no load
the
speed
no-load
has
speed
dropped
has dropped
because of the
because
armature
the armature
resistance.
resistance
This
is
expected,
expected,
but the no load
but the
current is
no-load
same
current is same
because the no
because
load
the
torque is
no-load
the
torque
same.
is the same.
Okay. Now
Now,
first part we
first
have
part
done.
we have done.
Second part
Second
is
part
on
is
load
on-load
speed
speed
after
after
connecting
connecting
the
the
3.5 ohm
3.5 ohm
resistance.
is.
See,
See,
it has been
it
given
has
that
been
the
given that
load
the load
is a
is a
constant torque
constant
load,
torque load,
and our no
and our
load
no-load
torques
torques
are also
are also
constant.
constant.
So
So
again,
again,
it will
it
draw the
will draw
same
the
line
same
current,
line current,
not line
not
current,
line
same
current,
armature
same
current,
armature current,
25
25
ampere
ampere,
with the
with the
armature
armature
series
series
resistance
resistance
connected,
connected,
because the
because the
torque
torque
that is has
that
to
is has to
supply, that is
supply, that is
constant, that has
constant,
not
that has
changed.
not changed.
So
So
torque is
torque is
Phi
phi
I will also be
I
the
will
same.
also be the same.
We have to
We
find out the on
find out
load
the on-load
speed.
speed.
Okay,
Okay.
first of all we
First
have
of
to
all, we
find
have to
out
find out
the on
the
load speed
on-load speed
when there
when
was
there
no
was no
armature
armature
resistance.
resistance.
25
25
ampere.
ampere.
So
So
back
back
EMF was
EMF was
220
220
minus
minus
12.5,
12.5,
which is
which is
207,
207.54.
207.54, right?
Right?
This is the
This
back
is the back
EMF
EMF
on load
on load
without armature
without armature
resistance.
resistance.
We have to find
We
out
have
the
to find
speed
out the
here.
speed.
On load, what
On
was the
load, what
speed?
was the speed?
Do we need to find out? No, we need not find out.
No, we need not
Sorry,
find out. Sorry,
we need not find out.
we need not find out.
Let us do it
Just
on
do it
load
on load
with the armature
with the armature
resistance connected.
resistance connected.
So 220
So
volt
20
here,
volt here,
25 ampere
25 ampere
flowing,
flowing,
100 volt
100
drop.
volt drop.
So the
So
new
the
speed
new
is now,
speed is now,
new
new
EMF is
EMF is
120 volt.
120 volt.
Can you not
Can you
find
not
out the
find
new
out the
speed?
new speed?
See, our
See,
back
our back
EMF is
EMF is
K phi
K phi
omega.
omega.
K is
K is
constant,
constant,
flux is
flux is
unchanged.
unchanged.
So
So
previously when we
previously when
had
we had
219 volt
219 volt
for
for
1100
1100
RPM,
RPM,
this same
the same
relation
relation
we can still
we can
use.
still use.
Means this
Means the
same
same
set.
set.
Okay. Equal to
Equal to
1100
1100
by
by
N2.
N2.
What is
What
N2?
is N2?
N2 is 120 times 1100, 601.
601.
So with the
So with the
armature
armature
resistance connected,
resistance connected,
when there was
when
no
there
load,
was no load,
it was
it was
this much of
this
speed.
much of speed.
On full
On
load,
full load,
the speed
the
has
speed
dropped
has
to
dropped to
this.
this.
We have
We have
been asked
been
to
asked
find
to
out the
find
speed
out the speed
regulation.
regulation.
So
So
percentage speed
percentage speed
regulation
regulation
is nothing
is
but the
nothing but the
difference
difference
by the base
by the
speed.
base speed.
In this
In
case,
this case,
we have to
we
take
have to
this
take
one,
this one.
no load.
No load.
Whatever you
Whatever
get,
you
around
get, around
44%, they have
44%, they have
probably was doing it. Yes, 44%
44%.
we will get. So the third
So the
question,
third question,
estimate the speed
estimate the speed
regulation
regulation
of the no
of
load
the no
speed
load speed
after
after
connecting
connecting
the
the
resistance. This is
resistance. Means
44% drop in
44% drop
speed.
in speed.
This speed,
This speed,
um, okay, let us do
let
one
us do
thing.
one thing.
Let us find
Let us
out this
find out
speed
this
also.
speed also.
When there
When
was,
there was,
this is not
this
asked
is
in
not
the
asked in the
question.
question.
We'll just see.
We'll just see.
Uh,
Uh,
on load
on
speed
load speed
with the armature
with the
resistance
armature
connected.
resistance connected.
The same
The same
way I will
way
do.
I will do,
I'm not
I'm
writing
not
anymore.
writing anymore.
Just calculating
Calculating
207.5
207.5
times
times
1100 by 219.5,
1039.
1039. Sorry,
So
RPM. What was the percentage regulation without the resistance? So I am writing it R ohm. Means this is not a standard notation, I'm just writing. Percentage regulation with resistance, and without resistance it is 1100 minus 1039 by 1100. How much is it coming? I am doing this to show you one thing. It's only 6%, 5.5%. So what do you interpret out of it? More armature resistance you have, the drop on loading is more. So if you have torque speed characteristic, it is like this, straight line, drooping straight line. And if you connect series resistance, it is like this. Sorry. It drops faster. So if you have increased armature resistance, then on loading the machine, the speed will drop very fast. This is what I wanted to establish. Any question, or else I will stop for today. Okay, I will stop. Shashidhar, do not leave.
No, so I can